Hi there, my name is Kelvin, and in this video we'll present our work on simultaneous visibility representations of pairs of undirected graphs. This is joint work with Ben Chugg from Stanford University and Will Evans from the University of British Columbia. Suppose we're given a graph G equals to VE. A popular representation of this graph is a visibility representation, where its vertices are drawn as connected shapes on the plane and its edges become uninterrupted lines of sight between the shapes. For example, here we have drawn the vertices of G as axis-aligned rectangles, and the edges of G as axis-aligned horizontal visibilities between the shapes. Now suppose we're given a pair of graphs instead, and in particular, we assume that the two graphs share a common vertex set. A natural extension of the visibility representation for one graph is a simultaneous visibility representation for a pair of graphs. Here, vertices are still drawn as connected shapes on the plane, but the edges of one graph are now depicted as vertical visibilities, while the edges of the other graph become horizontal visibilities. Both visibility representations and simultaneous visibility representations have a wide literature in graph drawing. For example, Stranu and Whitesides described a beautiful connection between a pair of directed planar graphs and their planar duals that determine whether they have a simultaneous visibility representation using rectangles. This connection was later extended by Evans, Liotta, and Montechiani to the case of L shapes, where the orientation of each shape is given by some function phi. In both of these cases, the authors found polynomial time algorithms to determine whether a pair of directed graphs has a simultaneous visibility representation. However, the question of whether such an algorithm exists for a pair of undirected graphs remains an open problem, and this will be the focus of our talk today. So here are our two main results. Roughly speaking, our first result is a hardness result that says that deciding whether a pair of undirected graphs has a simultaneous visibility representation is NP-hard. Now, what's interesting about this result is that our graphs that we used in our proofs were fairly simple ones. And so this result really limits the families of graphs for which we can reasonably hope to efficiently determine a simultaneous visibility representation. This motivates our search for a family of simple graphs for which this is possible. In our second result, we give a linear time algorithm to decide if a pair of undirected graphs has a simultaneous visibility representation using fixed orientation L shapes. Ben will discuss this result in much more detail in the latter half of this talk. But to get things started, let's first take a quick look at our hardness result. Just to reiterate, our hardness result shows that deciding if a pair of undirected graphs has a simultaneous visibility representation is NP-hard. And there are three things we'd like to note about this result. First, this result holds for a variety of shapes, including L shapes, rectangles, unit squares, and many others. Second, for some simple constant complexity shapes like L shapes, rectangles, and unit squares, our results can be further strengthened to NP completeness. And finally, our result holds for remarkably simple graphs. In particular, for L shapes and rectangles, one graph is a set of disjoint paths, and the other is a set of disjoint spiders. And in the case of unit squares, our graphs get even simpler. One graph remains a set of disjoint paths, and the other become a set of disjoint claws instead. To gain some intuition for our proof, let's walk through a quick example of a reduction for unit squares. So here's a three-set formula, and in particular, this is a monotone three-set formula, since each literal is an unnegated variable. Our goal is to determine whether there is a satisfying assignment for this formula, such that the three values in each clause are not all equal. This is known as a monotone not all equal three-set problem, which we know is NP-complete due to Schaeffer's dichotomy theorem. Our reduction is based around reducing from this problem to our problem of deciding whether a pair of undirected graphs has a simultaneous visibility representation using unit squares. And this is how our reduction is going to look like. In our first graph, we start by building a clause gadget, which is a path connecting one vertex in each clause in our formula. We can also do the same for the literals representing the same variable, which forms our variable gadgets. So for example, here we have a path for V4 and another path for V2, and so on. Now, the idea behind these gadgets is that they will enforce some form of consistency between the vertices joined by each path. So if we drew this graph with horizontal visibilities, then we get these bands of horizontal visibilities, shown here in gray, that cannot cross each other. This allows us to encode the truthfulness of each variable by whether its band lies above or below that of a clause gadget. For example, here we have encoded V2 and V4 as true, and V1 and V3 as false. Of course, we still need to enforce satisfiability here. And to do this, we build a second graph consisting of a claw for each clause that joins a central clause vertex to its literals. This graph is depicted here in red on the left. And we will draw this graph with vertical visibilities on the right. Now, what's interesting about these claw gadgets is that they can only be drawn in one of two ways. First, we can have exactly one square on top of the clause vertex and two below, as we highlight here in our green box. Or we can have one square below the clause vertex and two on top, as shown here. Thus, we can enforce that every clause has exactly one or two literals that are set to true, if the pair of graphs indeed admit a simultaneous visibility representation. So if our formula has a not all equals satisfying assignment, we should be able to draw a simultaneous visibility representation for our gadgets, as we have done so here on the right. This gives us one direction for our proof. For the other direction, we can simply note that a not all equal satisfying assignment can be easily determined from the simultaneous visibility representation by looking for which variables are drawn above the clause gadget and which ones are drawn below. And roughly that's it. We have just shown that deciding whether a pair of undirected graphs has a simultaneous visibility representation using unit squares is NP-hard. Next, I'll hand it over to Ben.
Okay, so we saw the reduction above uses relatively simple graphs, graphs that aren't actually much more complicated than paths. And so this is going to motivate our next question, which is going to be, for which shapes can we do simultaneous visibility recognition for two paths in polynomial time? The two paths we're going to denote as PH and PV. PH is going to be an enumeration of 1 through n. And when I say the PH is the horizontal path, and that's going to represent horizontal visibilities. Whereas the vertical path, PV, will just be some permutation on n, and that will represent vertical visibilities. So the first shape, which we might try to deal with, are rectangles. Rectangles are relatively simple because they can't share both a horizontal and a vertical visibility. So if the tuple I and I plus 1 is in the vertical path, then there's no way that an SVR of these rectangles exists. If this isn't the case, we can sort of just run this cute little algorithm in which we put the corner of gamma I, the ith point, we give it an x location of its ith position, the position of I in the vertical path, and a y location of I. And so as we see in this example, as long as there's no tuples like I and I plus 1 in the vertical path, this gives us a valid simultaneous visibility representation. So that gives us a necessary and sufficient condition for rectangles. Okay, so what if we start considering a shape now that does not have the property where two shapes cannot share both a horizontal and a vertical visibility? So what we're going to do is we're going to take the rectangle, we're going to remove the top and the right-hand side of the rectangle, and we're going to be left with this sort of this L shape. And these can be nested, so this is going to be a more difficult problem to solve. And that's what's going to take up the rest of the talk. And so formally, the question is, can we decide in polynomial time whether these two paths, PV, PH, admit what we're calling an L-shaped LSVR, or an LSVR for short? So instead of looking at an LSVR as sort of like a defunct rectangle, we're actually going to look at it as the union of two bar visibility representations. So a vertical bar visibility representation and a horizontal one. And a bar visibility representation is just a drawing in which the vertices are represented as lines, and then lines of sight are or straight lines between the bars. And these BVRs, these bar visibility representations of paths, have this sort of like nice monotonic structure. So if we lay out sort of gamma 1 on the left side and gamma n on the right side, they can always be made monotonic in the sense that the right-hand side of each bar of gamma I is always greater than the right-hand side of gamma I minus 1. And so it's sort of monotonic to the right in this case, monotonically increasing. It could also be monotonically decreasing, so it could also go from right to left. So each of the BVRs, the horizontal and vertical BVRs, can be monotonic in two ways. The vertical one can be monotonic from left to right, and the horizontal one from up to down. And so because an LSVR is a combination of two BVRs, we see that the LSVR can sort of be monotonic in four directions. And so we're going to have this sort of formal technical claim where we show that any LSVR of two paths, though it might not be drawn in this canonical way in which its two underlying BVRs are monotonic, it can always be made as such by sort of a continuous transformation by pulling or retracting bars. So in this example, we see that the original LSVR has sort of a weird, sort of this wild structure here where there's not much we think we can get out of it, but on the right, we see that after some pulling and stretching and contracting of the bars, we can get to an LSVR that is in fact monotonically increasing in both the horizontal BVR and the horizontal BVR. And so this result is nice. It kind of only allows us to deal with these quote unquote canonical LSVR, where canonical here just means that both the underlying BVRs are monotonic. Okay, so now we're just gonna focus on these four monotonicities, and we're just gonna fix one of them because the results are sort of symmetric. And now we're just gonna try running the previous algorithm that we did with the rectangles. And so we see in this case that this can give us a result with crossings, but unlike in the rectangle case, we can actually fix them. So these crossings among these three shapes on the left of the drawing can be fixed by sort of iteratively pulling the shapes to the left. And then these crossings at the bottom can be solved by pulling gamma 2 downwards. And so in this way, we started with a cross drawing and we come to this drawing, which is uncrossed. Okay, but this only works if the drawings can be uncrossed. So the next question is, are there any cases in which these crossings can't be alleviated by just pulling these things? And the answer is yes. And so here on the left, we have sort of the smallest example of a drawing with a given monotonicity that can't be alleviated in this way. So here, trying to pull gamma 3 downwards would block the vertical visibility between gamma 1 and gamma 2, and trying to pull gamma 2 to the left would block the horizontal visibility, or the vertical visibility rather, between gamma 1 and gamma 3. And so here we note that we can't pull left because it would block this vertical visibility, and this vertical visibility is in place because the monotonicity of the horizontal bar. So because the horizontal bars is below, that's why we can't pull it back. So we can't cross because of conditions on the underlying bars, because of the monotonicity. And so for this monotonicity, we're going to call such a condition a forbidden condition. And each orientation has a forbidden condition that we can codify. And so this, because each LSVR has one of these four orientations, we can say that an LSVR will exist if and only if one of these four forbidden conditions, at least one, is not met, and meaning it will not exist if all four forbidden conditions are met.